Derivatives of Laplace transform or multiplication by powers of t. We have proved this theorem for n is equal to 1. As I have told you, this theorem can be proved in the two cases. Case number 1, when n is equal to 1. Case number 2, when n is equal to r. Today we will have to prove this theorem for n is equal to r. As you know, the statement of the theorem of the derivatives of Laplace transform or multiplication by powers of t is, if the function ft is function if the function ft is sectionally continuous and as well as it is a function of exponential order, in that case we can prove Laplace transform of t raised to power n ft is equal to minus 1 raised to the power n dn upon dsn fs, or in other words, Laplace transform of tn ft is equal to minus 1 raised to the power n fn s. Here in this case, the value of 1 n is equal to 1, 2, 3 and so on. So this is the theorem of the derivatives of Laplace transform or multiplication by powers of t, and we have proved it for n is equal to 1. Case number 2, when n is equal to r, we can prove the same as follows. So if n is equal to r, in that case expression will be minus 1 whole r f r s is equal to Laplace transform of t raised to power r ft. Now differentiating with respect to r, we have minus 1 raised to the power r f r plus 1 s is equal to 0 to infinite del upon del s, then tr e raised to power minus st ft and then dt. If we solve it, we will have 0 to infinite t raised to power r ft, then del upon del s e raised to power minus st, then dt. or we can say it is 0 to infinite t raised to power r f t, then minus t e raised to power minus st dt. Or in other words, minus 1 raised to power r plus 1 f r plus 1 s is equal to 0 to infinite t raised to power r plus 1 e raised to power minus st ft dt. This is minus 1 r plus 1 del r plus 1 f, then this is s upon del s r plus 1 is equal to Laplace transform of t raised to power r plus 1 ft. So this proves that the theorem is true for n is equal to r plus 1. If it is true for n is equal to r, but we have already proved that the theorem is true for n is equal to 1, and hence for n is equal to 1 plus 1, that is 2, it will be 2. Similarly, therefore n is equal to 2 plus 1 is equal to 3, it will be 2, and so on. Hence, it is true for any positive integer. That is, this process shows that the theorem is true for n is equal to r plus 1. We have proved that this theorem is true for n is equal to r plus 1, provided that it is true for n is equal to r. This we have proved. Now we have already proved that this theorem is true for n is equal to 1. It means it will be true for n is equal to 1 plus 1, that is 2. Therefore, it will be true for n is equal to 2 plus 1 is equal to 3, and so on. Hence, this theorem is true for any positive integer. Thank you.